All right, so in this video, we're going to take a look at a couple more examples now in dealing with the independence of path for line integrals and conservative vector fields. So we'll start here with our line integral, and you can see this would be the f dot dr that we mentioned. In this case, f is going to be that 2xy and then the x squared plus cosine y. And so first things first, we need to determine if that vector field is in fact conservative. So partial p over partial y needs to equal partial q over partial x, where this is p and this is q. So if we take the partial derivative of p with respect to y, we get a 2x. And now we just need to confirm that it is in fact equal to partial q with respect to x. And it is. This would be a constant, and that gives us our 2x. So therefore, this is conservative. And since this is conservative, now we can compute this line integral using the fundamental theorem from line integrals mentioned in the first video. What that boils down to is evaluating the potential function from this point minus this point. So everything rides now on finding that potential function. So we know, once again, that the vector field f being conservative is equal to the gradient of f, which is partial f over partial x, partial f, partial y. And so that means this is partial f, partial x, and this is partial f, partial y. So I'll take one of them, and again, it doesn't matter which one you start with, but I'll, in this particular case, take my partial f, partial x as 2xy. And I'll go ahead and integrate both sides. And this is going to be integrating with respect to x as that's been moved over. On the left, I'll have my f of xy. And on the right, I'll have my x squared y plus c of y. Remember, this being a constant has to be a function of y since we integrated only with respect to x. All right, so now from here, using that f of x, using the f of x, we want partial f, partial y. If we take partial f, partial y, that's going to give us an x squared plus c prime y. Now again, this was found using this. But we also know that partial f, partial y from above should equal this guy. So I'm going to set it equal to x squared plus cosine y. The equation now that I'm solving is right here, and clearly that would imply that c prime y equals cosine y. So to figure out what my c of y actually is, I'll go ahead now integrate both sides. And so c of y is actually going to equal sine of y plus c. And that will truly be a constant now since we've gone with respect to both x and y through this process. So all I need to do now is come back up here, finish off this potential function as an x squared y plus sine y plus c. And as I pointed out in the last video, you can always check your final answer. Take the partial of f with respect to x, you should get this. Partial of f with respect to y, you should get this. Now, in this case, they actually want us to compute this line integral. So the fundamental theorem says that we'll just go ahead now and take f of pi over 2 minus f of 0, 0. And so you're plugging this in for x and this in for y. You're plugging this in for x, this in for y here. And so it all boils down to the final answer of pi cubed over 2 plus 1. So in context, what we could say is the amount of work required for a particle to travel from this point to this point through this vector field is this guy right here, completely irrelevant of the path taken. All right, so now we'll take a look at the case where we have a vector field of P, Q, and R now. And so to show it's conservative, there's going to be a few additional steps, but all of which are pretty straightforward and pretty easy. So to show something's conservative, if you have the PQR vector field, you're going to have to show these three conditions. And so this being our P, this being our Q, and this being our R, if I take partial P with respect to Y, right here, that'll give me a -1. And if I take partial Q with respect to X, that also gives me a -1. So far, so good. Moving over to this guy, partial P with respect to Z would also be a -1. And partial R with respect to X is our -1. And then finally, partial Q with respect to Z. Partial Q with respect to Z would be 0. And then partial R with respect to Y would also be 0. So since all three of these check out, we can now say that F is conservative. If F is conservative, now we can move forward with finding that potential function. So to find that potential function, again, this is partial F, partial X, partial F, partial Y, and partial F, partial Z. I know that because F equals the gradient of that potential function. So in the last several examples, I went ahead and I started with partial F with respect to X just to mix things up and give you a variety. I'm going to start this one with partial F, partial Y. It doesn't matter where you start, but you are just going to have to make the adjustments along the way. So partial F, partial Y is going to be 2Y minus X. So now I'm going to go ahead and integrate both sides, and this is being done with respect to Y. So that's going to be f of xy equals a y squared minus xy plus some constant. Now remember, I was integrating with respect to y, so the constant now is going to be, or could be, with respect to x or z. So you have to make sure to include the correct potential variables that could come out as a 0 when we take that derivative. And feel free to work backwards. Take this derivative with respect to y, and you should get this right here. All right, so now from this, I'm going to now need to find either partial f partial x or partial f partial z. Once again, it doesn't matter. I'll go ahead and do partial f partial z. So finding the partial derivative of this with respect to z is going to give me a 0, 0, and then just a c prime right there. So c prime of xz. So this blue stuff was found from this. Now I will go ahead and set it equal to what it should be up here as the 2z minus x. So 2z minus x. So from there, it's pretty clear that c prime, that c prime equals this. So I don't really need to carry that down any further. I'll go ahead and integrate right here. And remember, when you're integrating with respect to z. So you're integrating with respect to z. So we'll have our c of xz equals, that'll be a z squared minus xz, and then plus c of x. We had to have new constant now, c of x. We integrated with respect to z. And once again, if you take the derivative of this with respect to z, you should end up with this as we would, with this being c of x. All right, so let me move this up a little bit. And we're ready now to say that f of xy equals y squared minus xy. And then that's going to be a plus z squared minus xz plus c of x. So this stuff right here, and then my c of xz, I replaced with that right there. Now, we need to continue on. I'm going to go ahead and move down now and take the partial of f with respect to x. So straight from here, coming down, partial with respect to x is going to give us a negative y minus z plus c prime of x. So there's our negative y, there's our negative z, and then there's our c prime. I'll now take this and set it equal to what it should be right up here. So 2x minus y minus z. And this is going to tell us that c prime of x is going to equal 2x. if I go ahead and integrate that now, my c of x will be an x squared plus your normal constant c. And so I'm ready to come up here now and put this all together. My f of xyz is going to be y squared minus xy plus z squared minus xz plus x squared plus c. So for that step there, all I did was I took my c of x and replaced it right there. And so that being now brought up to there is our potential function. If we were to need to evaluate, we certainly could, but this is our potential function. And as you walk away from this, I would encourage you now to take this, find the partial of f with respect to x, and you should get that. Partial of f with respect to y, you should get that. Partial of f with respect to z, you should get that. The only other things to keep in mind is that as you move forward with this, just remember what variable you're with respect to and integrating, and what you need to keep your constants with respect to as well. That's really going to be the only difference in a problem like this, as deciding where you want to start and then keeping track of all of your constants.